This is lecture 16. Nothing new in this lecture except introducing experiment 6, and then later we'll tack on an example problem here. So this is experiment 6. It's probably the most involved in experiment, or at least it can be, depending on how well you implement the thing. So more details later. And so the issue is this experiment. Essentially, you're going to add one module, which is a very simple module, and then you're going to modify the two control units to support the rest of the instruction set. So right now we've supported 5 or 6 instructions. You're going to modify those control units to support the rest of the instructions. So, and once you get that built, of course, you're going to test it in hardware, and more details on that later. So this is the branch condition generator module. It's a module that is up in the upper right corner. Essentially, it's going to provide input to the control unit decoder. Now, these inputs here are going to support the branch instructions. So all the branch instructions we have are based on comparisons. This box here is essentially a comparator. It looks like a comparator. It has 2 inputs and 3 outputs, as comparators we know and love. It's a little bit different. Essentially, it has to handle both signed and unsigned math. And so this is the simplest comparator we can come up with. You have a couple choices on this. You need either implement it as one box, or you can actually use 3 assigned statements and not use a module for this. Either way, the issue is these 2 outputs here are outputs from the register file. These will be inputs to the control unit decoder. And specifically, the branch instructions are going to use these inputs to decide whether to branch or not, which is why they call it the branch condition generator. So this is the branch condition generator. You can see it gets outputs from the register file. These outputs are fed into the control unit decoder. Notice it doesn't attach to the state machine part of the control unit. And so, yeah, once again, this is effects of essentially this PC source here, and essentially based on these input signals, it's going to tell the microcontroller to take the branch or not. So essentially, it's going to output is either going to be 0 or 2. If it takes the branch, you got the 2 output there. This is exactly what controls that functionality. So the approach you want to take in this one is first create the branch condition generator module and add it to your microcontroller. Now, from experiment 5, your hardware should be very complete. This should be a very quick change. It's a very minor module, or it's just 3 lines of code depending on how you implement this thing. Next thing you have to do is implement all your instructions. You got about 35 more to do, or something like that, and then once you get all those implemented, you're going to test it on your board. Now, I just always hope that when you do this, it just magically works the first try, but in case it doesn't, it might not, you're going to have to debug it. And so whatever the notion here is, we provide all the support files for you, and provide a lot of everything so that you can debug it yourself. Okay, so in experiment 6, you have to be aware that we are using different hardware for this thing other than the microcontroller. Okay, so your microcontroller is what you're using from the previous experiment, but the wrapper and everything else is different. Now, this experiment is not mine. This is from the original people who used this experiment, and that's why it's a little bit different. So you have to toss out everything you had before except your microcontroller and use all the provided modules. So all the modules are on Canvas, of course, and so the issue here is once you toss all those modules together, there's a program, and so essentially it's the machine code. You don't have to worry too much about the assembly code for that, but there's a machine code, and what you're going to do is put that in your auto_memory.mem file, and fire it off, see if it works. And so here's the issue here is this is the machine code that you're going to put in your project. This is how it's named on Canvas. This is the assembly code that generated it, and this is a listing file. Now, once again, these are all three on Canvas. The listing file is going to help you debug this thing, and I have intentions of making another video to show exactly what's in that listing file. So if it doesn't work, you're going to have to figure out why it doesn't work based on what it should be doing, and what it should be doing is listed in either not the machine code, but the test code, which is hard to read, but more so the listing file. The listing file is going to be pretty much the key file you work with in this experiment, and like I said, I'll put some stuff out there on that later. So the last thing here is there's actually two testing files. This right here is a memory machine code file also, and so you can use this if you change that. Now, if you change the name of this thing, of this file, to otter_memory.mem. So what happens is, if you have an error in this file, it just kind of blinks a 1 or a -1, I can't remember. But if you have an error using this file, when you have an error, the program stops, and you can see the number where it stopped on. So it turns out there are about 37 different tests in this program, and it runs through each of those tests, and if there's an error, if there's not an error, it turns an LED on. If there is an error, I think it just skips to the next test after outputting like a 1 or something on the display. So you'll know when it's wrong, and there's a video out there that shows when it's right. So this is, I always toss this table out here because this is how you're going to implement the instructions. And I honestly, I've never really used these things, but students like using them. And so this is how you work this table is for any given instruction here. These are all the control signals coming out of the control units, both the decoder and the FSM. And so once again, these are all outputs of the control unit FSM. So actually we can circle that. This is the FSM outputs, and this is the decoder output, DCDR. And so you can actually go through this table and fill these out one by one, etc., etc. What you'll see here, and I think this is coming up, is a lot of these signals are the same. Okay, so you're gonna, for this experiment, you're gonna exploit the sameness. Here it is, exploit the sameness in these instructions in both the control unit and the decoder. So the control unit, it has about 9 different instruction types. Essentially, that means it's essentially going to be a case statement with 9 different, clauses in it. And the control unit decoder, not much different. I know there's 40 instructions or 35-ish. You've seen it before. It's a lot of the instructions are very similar across instruction types, etc., etc. You're gonna hopefully see that and exploit that. And these files can be extremely short. I've seen them like fit on a page if you know exactly what you're doing, and I've seen students make it like 6 or 7 pages. You should shoot for 2 pages, exploit the sameness in it, and that goes for both these files. And I will say, yeah, just you don't have to go overboard on it. I think when I did this, it was like 2 pages long. That's a decent something you should shoot for. You don't necessarily need to shoot for 1 page on this thing, but whatever, it doesn't matter. However you do it, it's going to work. Most importantly is you just understand what you're doing when you're doing this. And I will say that is it. So once again, there's a video out there. Check the video out of the working hardware. That's going to get you going. That's going to see what you expect from the working hardware, at least the program that's driving the hardware.